Are y'all red eye? We're red eye. We've
Red
been
eye.
tired.
We are red.
Okay, here we go. Other identities. Yes, children, there are more and more and more. You know, we're not making you memorize nearly as many as there actually are, so be happy. All right, double angle identities. These are identities where if you know an angle and you double it, it reduces down to this. Okay, now how do we get, for instance, sine of 2x equals 2 sine x cosine x? Some of you guys are still trying when you see a 2 here or here or here. You think you can factor that out, but let's just pretend we're making brownies and you put 2 eggs into the mix. Guess what?
They can't come out.
They can't come out. They're already in the function mix of making brownies. So you cannot do that. But what we do have is a neat little way to derive this formula. So if you will follow with me a little farther down in your paper, I am going to label each of our x's as 2 different colors. So here is my green x, and here is my red x. So my sine of 2 x's, I'm going to just differentiate between the 2 x's. Our identity for sine of 2x, if we take this as your, like your a, let's remember sine of a plus b is sine a and cosine b. Same sign. Sine has the same sign. Plus cosine a sine b. Okay? That's the identity we're going to use. So, sine of the first term in the polynomial is the green x. So, sine of green x times the cosine of the red x plus cosine of the green x times sine of the red x. And look what happens. I have got sine x, cosine x, sine x. Each of those x's are the same, really. I have, because an x is an x is an x, and they're the same value. And notice, I have sine cosine plus cosine sine. Is it true that 2 times 3 is equal to 3 times 2? Well, sure it is. So I can just add 2 times 3 plus 3 times 2 makes 2 times 3's. And that is what you have here. Okay? So, and when you have a product, it doesn't matter what order you multiply it in. Sine times cosine or cosine times sine gives the same thing. I'm adding 2 things that are the same, hence 2 sine x cosine x.
Yes.
All right? Now, you really need to know this one. This is pretty important. Okay, this sine x one. That's a really important one. And the other one you really need to know without thinking about it is cosine of 2x. Cosine is their double angle formula for cosine. There are 2 other identities that come from that one that you can generate. So this is the one that's in this box that you need to memorize. And once again, you have tangent of 2x equals 2 tangent x over 1 minus tangent squared x. You could eventually get there by taking sine of 2x over cosine of 2x and doing a ton of algebra. You could eventually get there, but it's, in this case, easier to memorize that one, but not nearly as important as the other 2. Okay, so here we go. First thing we have to do is pay attention to which quadrant we're in. And we're going to find, find sine of 2x and cosine of 2x. Now here's what we know, okay? And then, by the way, we're going to show that 2x lies in the right place. All right, so what we know here is that x, between pi and 3 pi over 2, we're in quadrant 3. Why is that important? Because in quadrant 3, cosine is negative and sine is negative. And here, so we are going to now find our value for sine of 2x. Sine of 2x is, what's the formula?
2 sine x cosine x.
Okay, so what we have is the cosine. Oh, 24 over 25. Since we're in quadrant 3, we're going to have to sine negative 24 to x, which makes our radius 25. And if you haven't memorized this Pythagorean triple, then more power to those who have, and shame on you who haven't, but this is one of your lesser used, but you should know it anyway, Pythagorean triples. 7, 24, 25. That means y has to be 7, but we're in quadrant 3, so it's negative 7. Okay, so we have the sine of our angle, and now we're ready to go. Sine of 2x equals 2. The sine of our angle, don't know what x is, but we know that the sine is the ratio of y to r. So 2 times negative 7 over 25. Notice the use of the parentheses because we have a negative sign there. And cosine is negative 24 over 25. Now, back in the fall, we told you, well, at least I told my students, I don't know, but you should know the squares from 1 to 20. 25 may not be one you've memorized, but to be honest with you, you should know that it's 625. So if you don't know that, please memorize it. You know, you need to know 1 through 20, and then 25 is a pretty good one to know off the top of your head.
And the tens, all the tens.
Yeah. Okay, so I am going to do 7. A negative times negative makes positive, and I'm going to go ahead and do 2 times 24 because I can do that particular multiplication in my head without much difficulty, and then we're going to multiply the 7 times the 48, and you're going to get 336 over 25. Now, 625, excuse me. That is the sign of 2x. Don't ever just leave it blank there. Okay, first of all, here is something we're supposed to show. We're going to have to show that 2x is between 2 pi and 5 pi over 2, which basically means one rotation around the circle. We're at 2 pi. And 2 pi, some of you, this is another thing we're not going to answer questions on. You can't do that particular addition. And we just don't understand how you cannot take 2 plus 1 half and not understand without thinking very hard that that is 5 halves. That's just unacceptable. Okay? You learned how to do that way back even before you were in middle school. Okay? So you need to know 2 pi, and this would be 5 pi over 2 with another rotation of the circle. Well, what am I going to need to show that it's 5 pi over 2? Well, I need sine and cosine to both be positive. There's part of it done right there. Sine is positive. So hopefully, cosine of 2x will also turn out to be positive. So here we go with cosine of 2x. I want to use a different color. Okay. Which formula shall we use? Oh, we haven't given the other formula, so we need to use this one.
Cosine squared x minus sine squared x.
Notice that is not cosine squared x plus sine squared x. Notice that? Okay. All right, so our cosine is what?
Cosine is negative 24 over 25.
Oh, no, there's another number we're going to have to figure out. Uh-huh.
And let's see, negative 7 over 25.
Oh, I was squaring it all already. That's dangerous because I might square wrong. So you always want to do your direct substitution first and then do the math, because if you make a mistake, at least you found a place to make it. Okay, if you know that 25 squared is 625, then 24 can't be too far away from it. It does happen to be 576. Okay? And since you're going to have this ratio of 724, this Pythagorean triple show up, 724, 25, it's probably useful to know the square of 24. All right? Minus, here is a mistake some of you still make. It is unacceptable.
Minus.
You do not have a minus here because the order of operations says we have to square that thing first.
When you square a negative, it is positive.
Okay, and that's just, again, at this stage, guys, you are in advanced math. You are pre-cal students. And that means you've gone above and beyond what many high school students across the country do. So our expectation for you is that you start using that brain that you are developing. Okay? You need to know this. This is not a mistake you should make. Don't make that mistake, okay? You know better than that, so come on, let's not make those. You're too smart to make that mistake. All right, so we do 576 minus 49. It's 527 over 620. You know, that's why we get frustrated. It's not because we're frustrated you don't understand something. Usually, we're frustrated because you know how to do it and you just won't make yourself do it. And that's when Ms. Miller and I get upset, when you guys don't perform to the potential that we know is there, okay? Because we do love you, really, I know. All right, notice our cosine of the double angle is positive. So, we have sine positive, cosine positive. The only way that can happen, sine of 2x is positive, and cosine of 2x is positive. Therefore, 2x is in quadrant 1.
Yep.
Much love.
All right, so next you're going to do the entrance ticket problem number 1 in section 9.3, number 24. No calcs, please. Whoa.
Oops. Okay, let's look at this one. What we're going to do here, this one gets very complicated. Okay, so we're going to divide it. we're going to make it into an A plus B.
Yep.
So let's write our cosine of A plus B formula above so we can use the pattern.
All right, so we have the cosine of A plus B equals the cosine of A, cosine of B. That's beta. Okay.
C means change the sign. Mm-hmm.
There's a parentheses missing there. Mm-hmm. Okay, sine of A, sine of B. Okay, and there we go. Another one that we're going to have to use later is the cosine of 2x equals cosine squared of x minus sine squared of x.
All right. And it also, as a side note here, make sure that when you do your cosine of 2x, that 2 is actually, you know, the product of 2x, and that 2 does not appear to be an exponent like the cosine squared on the other side. Please be precise, okay? Precision matters.
All right, so let's look at this. What is 3x?
2x plus x.
Yes. So I'm going to write that in my cosine. So the cosine of 2x plus x equals, this is a sum, so I'm going to use my sum property right here, the sum of two angles. So that equals the cosine of 2x times the cosine of x minus the sine of 2x times the sine of x.
Ooh, there's another identity we need. We need to go ahead and write sine of 2x up there too.
Yep, write that over here. So I'm going to write it right here. Sine of 2x equals 2 sine x cosine x. Okay. So now I'm going to replace, substitute in for cosine x, the cosine 2x, the identity that we saw up there. So we have in parentheses, very important.
Yeah, that's another thing we don't understand.
Cosine squared x minus sine squared x times, I'm not changing this one, cosine x minus, okay, I'm going to use the sine of 2x identity, and that is going to be, I don't really technically need parentheses here because nothing's being added, but I'm going to use them anyway. 2 sine x cosine x times sine x. Okay, now what we're going to do is we have at least one thing that can come out of both of these terms, and that would be cosine of x.
Yeah.
See, I've got a GCF here. In this term right here, I've got cosine of x.
Hey, could we have distributed that cosine if we
could.
wanted to? Though we're looking ahead.
We're looking ahead and saying, okay, I don't really want to make it more complicated with all of my terms and give myself 3 terms when I only have 2 here and they have a GCF. So I'm going to take the cosine out of both of these. So this gives me the cosine of x, that's what I took out, and the leftover stuff is cosine squared x minus sine squared x minus, what I have left over here is 2 sine squared x. You should be able to see that this sine and this sine will multiply to give me sine squared x.
Sine.
Okay? All right, next, I'm going to go ahead and since this parentheses doesn't have anything being multiplied to it, I can go ahead and just drop the parentheses. So this equals cosine of x times cosine squared x minus sine squared x minus 2 sine. This minus this is minus 3 sine squared x. So I just combined them. Okay? So now what I'm going to do is I'm going to go ahead and replace, I need everything to be in the same trigonometric ratio, a trigonometric function. And I've got a cosine and a cosine and a sine. So I'm going to use my trig ratio identity for sine squared. And that equals 1 minus cosine squared
No,
x.
your Pythagorean identity.
That's my Pythagorean identity.
See, we do this at 6:30 in the morning. We're tired.
Okay, so
Wait, how come we didn't do it for
cosine
squared instead of sine squared? Why did you make that decision?
Well, the reason that I did that was because I had a cosine here, and I can't change a cosine.
Unless we use like a ratio identity or
Which isn't
going to help us.
I don't want to change
a reciprocal
it to secant.
identity.
I don't want to change it to secant. So I have a cosine squared and a sine squared. Well, since the cosines match, I'm going to change the sign squared so that everything matches.
That's assuming you know your Pythagorean identities, and not only that you know them, but you know them in various forms. If you don't know them in various forms, you can't use them. You know, imagine not knowing how to make a left turn, and all you can do is make right turns everywhere you go. Well, that wouldn't take you a lot longer to get places, and sometimes you just wouldn't get anywhere. That's what you have to know. You have to know every form of these identities so you can use them properly and efficiently.
All right, so I just made my substitution for sine squared x. And now what I'm going to do is I'm going to go ahead and distribute that -3. So I'm in black, I'm going to write what I haven't changed.
Do you notice that she's still writing the things that are still there? She's not just leaving that off because she's lazy. She's actually keeping everything there that should be there.
All right. If you leave it off, you're going to have a negative mistake.
Yeah, and we're going to count off for it.
And it's going to be bad.
We're going to get mad because that's just an Algebra 1 error that our Algebra 1 students are not permitted to make.
Okay, so now we can combine like terms inside this bracket here. I've got a cosine squared x and 3 cosine squared x. So what I haven't changed, let me move that up a bit. I feel like I'm writing too low. All right, the cosine x times, I've got 4 cosine squared x, I haven't changed this, -3. Okay, well now what I can do is I can go ahead and, well this is far enough because I've simplified it enough and I've taken out the GCF. So let's bring down what this equals. Cosine of 3x equals cosine of x times 4 cosine squared x -3. Another way to think of this is cosine of 3x equals, if I distribute the cosine, 4 cosine cubed x -3 cosine x. Okay, so this one or this one. They're the same.
Now, here's a really cool thing about this problem. Why in the world would we leave it like this? Well, the next section that you're going to have in this class is going to do something like this. Insert a blank page, let's go. If we had, just for grins, cosine 3x is equal to, what was it, cosine x times 4 cosine squared of x -3?
Yep.
And let's say we wanted to find where that was equal to 0. Well,
now it's already factored.
Yeah, and so we like this form, cosine x equals 0, or 4 cosine squared x -3 equals 0. This should be easy. Cosine x is 0, where x is pi over 2, and 3 pi over 2. Let's say that we wanted to find all the zeros on the interval 0 to 2 pi. That shouldn't have to think about it all. But this one has cool little algebra. We're going to do 4 cosine squared x equals 3. Cosine squared x equals 3/4. You're going, I don't know a value for that, but oh you do, because cosine x equals plus minus the square root of 3/4, which amazingly
becomes a unit circle value.
Plus minus the square root of 3/2. So cosine of an angle equals positive square root of 3/2. X is the long side, so that's a pi over 6 angle. That happens at pi over 6 and 11 pi over 6, quadrant 1 and quadrant 4. Cosine of x equals negative square root of 3/2. That's in quadrants 2 and 3 with a pi over 6 reference angle. So x is 5 pi over 6 and 7 pi over 6. Now, some of you are sitting here being very baffled with how I got to those numbers so fast. That's what you're supposed to know now, and we're not going to help you with that anymore, so good luck. Okay.
All right, so did you notice that once again we use the Pythagorean identities for sine squared x and cosine squared x? We need to have those. We can use these as well as Pythagorean identities for cosine squared x to get more identities for cosine 2x.
Instead of sine squared x,
we can replace it with 1 minus cosine squared x, and now we have a bunch of cosine squared x's in there.
And we're going to distribute
Distribute the negative, and that makes the cosine squared x positive.
Woo, look at that!
We've got 2 things that we can add together, and that becomes 2 cosine squared x minus 1.
That is pretty nifty cool. Sometimes you need to know that one, okay?
And another one is if I replace the cosine squared x with 1 minus sine squared x, I can go ahead and subtract sine squared x from sine squared x and get minus 2 sine squared x, so I have 1 minus 2 sine squared x.
All right, now, do you need to memorize these? Your life will be easier if you know them, but honestly, you should be able to generate them when you need them. You will need to be able to use both. Okay.
Okay, so now we're going to prove something fun.
Yeah, this is cool. Ready? Which one should we use, Ms. Miller?
I think the left side is the more nasty, so
Okay.
I'm going to use the left side.
And which identity, given that I've decided to use that, which one do you think we should use?
Well, definitely one for cosine of 2x. Now, the question is, which one do I want to use?
I have 3.
Well, it needs to be one with sine in it, because in order for me to have an answer with only signs, I need to have an identity that I use that uses only signs. So let's use 1 minus 2 sine squared x.
Over.
Well, that's just our identity.
Oh, I'm a step ahead. Okay, there we go.
So there's our identity that we're going to use, okay? So we're going to go ahead and use that identity. So
we're going to work the left-hand side. Okay, here we go.
1 minus, and then put parentheses around it, very important. 1 minus 2 sine squared x over sine x. And
the equal sign. You don't have to write the right-hand side all the way down, but you need to have the equal sign so that you're keeping it clear, not only with us, but with yourself, which side you're working.
And don't write it from left to right. Work your work down, okay?
Vertically.
Vertical, please.
And by the way, you spell vertical C-A-L, not C-L-E. Okay.
All right, so this gives us 1 minus 1 plus 2 sine squared x, which equal over sine x. Yes, please write the denominator as well. Equals 2 sine x, sine squared x over sine x, because the ones cancel each other out, and over sine x, and then that becomes 2 sine x, because sine x over sine x is 1, and that is what we were looking for. Yay! And please don't forget your final statement, that they are equal. So go ahead and do number 33 from the Chapter 9 review on page 613. Okay.
All right, for those of you that do take calculus somewhere down the road, you know, some of you are going to take calculus in some class, but for some major for college. You're going to find yourself having to take it. So I would never throw all these notes out because you're going to need them down the road and you'll be glad you have them. Well, down the road, it's useful to have these power-reducing identities. All right, let's see how we got to them. If we take cosine of 2x equal to 2 cosine squared x and solve that for cosine squared, you can see that to solve that, we would add the 1, and then we're going to divide by 2. Okay? That's how we get to that one. If another way to do it is to take this identity where we have the 2 sine squared, and we're going to solve that for sine squared. Again, I find it easier to eliminate the negatives as much as possible, so you'll notice that I moved the sine squared to the right, to the left, and the cosine 2x to the right, so we get this equation, and then we're going to divide by the 2. Okay? Again, you can not have to memorize these and be able to generate them, but then that requires that you know these formulas, and if you don't know these two formulas, that requires that you know this formula. Again, all of those formulas or identities are generated from this one basic one. So if you don't learn the basic one, you'll never be able to do any of them. All right, so what we're going to do is express this function in terms of constants and first powers of cosines.
First powers. First powers. Okay, so we have f of x equals tangent squared x. The first thing we're going to have to look at is, oh, well, first off, I don't even have anything that has sine or cosine in it.
Hey, we could do tangent squared, secant 1 plus tangent squared,
no.
secant squared. Yeah, we could.
We could, but I don't remember that one very useful. That one's not as useful to me, but I do know that tangent squared x is sine squared x over cosine squared x.
Also, another reason not to use this one is it says to use first powers of
Yeah.
cosine. First powers means not second
Reducing.
power. Means not cosine squared. Okay? So, therefore, there's no reason we would want a tangent squared, secant squared, or anything crazy like that. So, don't use that identity. Again, got to make sure you know what you're being asked to do.
Okay, now what we do know is that the cosine of 2x, do you want me to just use the ones above
that
it?
one. Yeah, do
Okay,
sine.
I'm just going to write out the ones that we are going to use. We've got sine squared x equals 1 minus cosine of 2x over 2. And the cosine squared x equals 1 plus cosine of 2x over 2. So I'm just going to use these two identities to go ahead and reduce the powers. So for sine squared x, I'm going to put 1 minus cosine of 2x over 2 divided by 1 plus cosine of 2x over 2. Oh no, I have a complex fraction. What should I do?
The denominators are the same. They're just going to go away.
Yay! Okay, so that means this equals 1 minus cosine of 2x over 1 plus cosine of 2x.
Hey, we did it.
Which
So we can
is exactly what we were asked to find.
And f of x, therefore, is equal to tangent squared of x.
Which is equal to 1 minus cosine of 2x over 1 plus cosine of 2x.
Hey, can I cancel the cosine 2x's now? I got them both on the top.
No!
I can cancel the ones and the ones, and the cosines and the cosines, and get a negative over a positive, which is negative. There we go. Our answer's a negative sign.
No.
Oh. All right, the math comedy tour has now ended.
Okay, so go to chapter 9, review, page 613, and work number 31. Alright, so we're done with this video, and I hope that you learned some interesting new stuff and realized that silly algebraic mistakes are hindrances to your learning process.
Yes, they are.
So, don't forget to bring your entrance ticket and your notes to class. See you guys later!
Bye.